In this lesson, we're going to briefly talk about circles. So the first thing that we're going to do, and we're going to do this for every conic section, is we're going to state the definition. So you'll see here that I've drawn a circle, and a circle is probably the geometric shape that you've worked with most of all. So this definition is probably pretty familiar to you, but we'll dissect it anyway. So a circle is the collection of all of the points that are equidistant from a single point called the center. Okay, so you'll see here I drew a circle, and on the inside I marked the point that is its center. And so what the definition is telling us is that if we take any point on the circle, anywhere at all, and we consider the distance from that point to the center, let me do a better job with this one here. All of these are the same. And you'll notice that I'm labeling these lengths with the letter R because that is called the radius of the circle. Okay? So that's the geometric idea, that if I take any point at all on the center of on the outside of the circle, and I look at its distance to the center, it's always going to be the same. But now let's talk about a little bit about sort of the algebra of circles. So rather than drawing just a circle in space, let me draw a coordinate plane, like so. And for the purposes of this conversation, I'm actually going to use a coordinate plane with a pretty large scale. I'm going to say that 3 squares make 1. And now I'm going to draw a circle here whose center is the origin and whose radius is 1. And I'm actually going to write that here. The center of this circle is the origin, and the radius of this circle is 1. And this circle is actually a very special circle. This is called the unit circle. So many of you are moving on to taking trigonometry in the spring. And in trigonometry, the unit circle is going to rule your lives for the first few weeks. So my question to you is, to start this conversation about circles, what is the equation of this circle? So in some sense, this is going to be the marriage of everything we've talked about this semester. If you have a curve, what does it mean to talk about its equation? It means to come up with an equation so that if a point is on the circle, it satisfies the equation. And if it's not on the circle, it does not satisfy it. So an equation, so let's find the equation of the circle. In other words, any point xy should satisfy this equation if it is on the circle. Okay. Well, let's see what we know. So I'm going to pick a random point XY on this circle. And what I'm going to do next is I'm going to draw in a couple of lines. So I'm going to draw in this line. So say it with me. What is that red length? How did I get it? I went from the origin to the point XY on the circle. Well, we just said over here that a circle is the collection of all points equidistant from a single point. So what we just said over here was that if you take the distance between any point on the outside of the circle and its center, you are going to get the radius. So since this point is on the outside of our circle and this is its center, this length is its radius, so this is 1. Okay, but how do I get X and Y in play? Well, I can draw this right triangle. In fact, let me use a different color, so like so. And again, say it with me. Pause the video and say it. What are the sides of this triangle? So what's the blue side? The blue side is X. It is the horizontal coordinate of that point. So this is X. What about the green side? Right, so the green side is the vertical coordinate of our point, and so that's Y. And so what we're looking at is we're looking at a right triangle whose legs are X and Y, and whose hypotenuse is 1. And what I want you to notice, and I'm not going to do this because I don't want to clutter my picture, but I encourage you to do it on your own notes or, on a different circle if you want. You could do this for any point on the circle. Any point on the circle, you can draw an analogous right triangle. It's going to be a right triangle where the legs are the coordinates of the point, and the hypotenuse is the radius, aka 1. And by the Pythagorean theorem, what we see here is that x squared plus y squared is equal to 1. So that, my friends, is the equation of the unit circle. The circle whose center is the origin and whose radius is 1. Now, you might be asking yourselves, okay, well, that's nice and all, but obviously not every circle is going to be centered at the origin, and not every circle's radius is going to be 1. So let's look at another example, and then after this example, we'll generalize. So I'm not going to use the big scale again this time. So here's a coordinate system. And this time I'm going to take a circle centered at the point 3, 2. So I'm going to take this point and I'm going to label it. And then I'm going to draw a circle of radius 4. Okay, so again, let me write that here. The center of this circle is the point 3, 2, and the radius of this circle is 4. Okay, well, I'm going to do exactly the same thing. I'm going to really lean into my definition. The definition says that a circle is the collection of all of the points equidistant from a single point called the center. So that means that if I pick any point on this circle, so I don't know, let's pick this one here and call it XY. And then if I consider the distance from my center to that point, That's the radius, and so that is 4. And so you can see the beginnings of what we did with our previous conversation about the unit circle. We said that we can build a right triangle where this is the hypotenuse and figure out what the sides of that right triangle are using the coordinates of the points. So we're going to do exactly the same thing. And you'll notice that it's not much more complex as an idea. Okay. So this is a right triangle. We want to get a right triangle going because we have the really, really strong piece of information about right triangles. We have the Pythagorean theorem, which says that the sum of the squares of the lengths of the legs of a right triangle is the square of the length of the hypotenuse. Well, the question becomes, what are the legs? Well, it was all really, really simple with the unit circle because the vertical side of our triangle was just the vertical distance from the point down to the y-axis. So that was just y. But here, if you look at this example, y would be the distance all the way down to the x-axis. But the green line here doesn't go all the way down to the x-axis. It stops short. How short? So pause the video for a second and think about this. How far from the x-axis is the end of this green line? You're right. This green line stops at the point 3,2. It doesn't go below it. So that means that this distance here is 2. So again, if it had gone all the way down, it would have been y, but it stops short 2 units. So in fact, the green distance is y minus 2. By that exact same token, right? If we're looking at the blue line, so if it had gone all the way to the y-axis, that would have been the x-coordinate of the point. But it doesn't go all the way to the y-axis, it stops short. By how much? So pause the video and think about what would be this distance. You're right. It stops at this point. So that means that it stops short 3 units. So again, if it had gone all the way to the y-axis, that length would have been x, but because it stops short by 3, the length is x minus 3. So what that tells us is, again, it's a right triangle, and the Pythagorean theorem applies to any right triangle, which we know the sum of the squares of the lengths of the legs is the square of the length of the hypotenuse. So that means that in this case, x minus 3, in fact, I'll write again, by the Pythagorean theorem, x minus 3 squared plus y minus 2 squared is equal to what? Pause the video and think about it. You're right. The Pythagorean theorem says the sum of the squares of the lengths of the legs is the square of the length of the hypotenuse. So we didn't really see it play out too dramatically in our first example because the radius was just 1. And when you square 1, you get 1. But here, the hypotenuse is 4. So the square of that, and I'll write 4 squared here, and that's 16. So we will have a video in a little bit where we do lots of examples of all different conic sections. But for now, I'm going to go ahead and end this one with a summary. And this summary is going to take what we've seen in these first two examples and lump them together. But if the summary is too much, like if it makes too big of a jump, then please come see me in office hours or come talk to Irina to really kind of understand why this is going to be true for any center and any radius. The equation of the circle centered at the point AB with radius r is x minus a quantity squared plus y minus b quantity squared is equal to r squared. So again, this summary makes a pretty big leap. We didn't do a ton of examples to get here. So I encourage you to come talk to me if you have questions about exactly how this summary came to pass. And that is the end of this video. Next up, we'll start talking about parabola.